Hey, welcome back everybody. Gary Simmons here for the Game Institute with lesson 30 of the Dead Earth game development series. In this lesson, we are going to take a bit of a break from writing our AI scripts because we've been writing AI scripts now for many lessons, and it would be nice to do something different. We are, of course, going to have to come back and finish off our AI scripts very shortly, but let's, for a lesson or two, go on a slight diversion and do something altogether a little bit more fun. What we're going to do in this lesson is we're going to create our camera lens blood image effect, which is going to be used to indicate to the player the current state of their health and when they're being attacked by zombies. And if I flip over to my current production version of Dead Earth, you can see what this effect looks like. It's an image effect, which means in this lesson we're going to learn how to write our own image effects, whereas up until now we've just been using the image effects that ship with Unity. And this is my image effect here. It's currently called Bleed Behavior, although I don't actually like that name anymore, so I'm probably going to call it something different when we create our version of this. Now, image effects are comprised of two parts. The first part is a standard mono behavior script that we have to add to the camera. And you can see, if you look at my camera's inspector, underneath the camera component, I don't just have my bleed behavior script, I also have several of the image effect scripts that ship with Unity. So I'm using bloom, anti-aliasing, contrast enhance, etc. So when we create our image effect behavior, it has to be implemented in the correct way so that it plays nicely with the rest of the image effect chain. The way this basically works is when the camera renders the scene initially, it doesn't have any of the image effects applied, and the scene is rendered to a render texture. That render texture then gets sent into each of these image effect behaviors, where each one has a chance to modify the image in some way. And now this is usually done via a custom fragment shader. And that's the second part of writing our image effect. We're also going to have to write a fragment shader. Now, unfortunately, I'm not going to be able to explain in depth how shaders work in Unity. The topic's just too big. It needs several training series dedicated to it. But I am going to show myself writing the fragment shader. I'm going to talk through what I'm doing. So if you guys understand how basic transformation and lighting works in an engine, then you should have no problem keeping up. And if you don't, I'll also point you towards some material that I wrote many years ago that is still available on the Game Institute website, which I would definitely recommend that you read. They basically show how a 3D model that is nothing more than a mathematical representation gets transformed into a 2D image on the screen. And we also talk about how lighting works. And all of these things are very relevant to Unity, even though the course is old and it's not Unity specific. So I'll point you towards that later on. And of course, one of the other things we're going to need to do is create the actual blood texture itself. I'm going to do that in Photoshop, and that's the first thing I'm going to do. I'm going to show you how I author the texture. Now, I'm going to give you my texture, but because I'm not a very good artist, I'm sure you guys will probably create much better blood textures than me, or you might decide to create several different variants of the blood texture to keep it interesting. So I'm going to give you my blood texture, but I'm also going to show you how I made it, because the way this effect works, the alpha channel of the texture needs to be created in a very specific way. And I'll show you what I mean. You see, what we don't want is a blood effect that simply tints the screen red, because it just looks rubbish. And we want this effect to essentially have bits of blood starting to show up at different times on the screen as the player's damage becomes increased or their health diminishes. So you can see what I mean. If I move this test blood amount slider all the way down to 0, you can see that there's no blood on the screen. As I move it up, we don't see the whole scene turn red. We just start to see little bits of blood appear, like this little bit of blood in the middle here, some splats around the outside of the screen here. And as we increase that, we start to see more blood appear. Now we're starting to see some blood splats show up around here and a little bit more over here on the left-hand side. Of course, if I move it up all of the way, it can go very red indeed. But the whole point of this is that when our player is walking around the scene, when a zombie attacks them, we're going to sort of see this go, like that. But then that's quite an extreme blood amount. But then we're going to see that blood amount decrease back down to what the player's health is. So providing the player's health isn't still 100%. If he's taken some damage, then when the player first gets struck by the zombie, we're going to see this big sort of blood effect, but then it's going to fade away. But if the player's health isn't 100%, we're going to see some of that blood stay on the screen, which is an indicator that the player is damaged and should be looking for a health kit or something like that. So it's really cool, right? Because once the player gets damaged, it's going to go like that, and then over time, as he's walking around trying to find a health kit, we're going to see the damage kind of dissipate, but not completely until his health is fully repaired. Okay, so let's talk about the artwork that's being used here. And in fact, what I'll do is I'll load the texture into Photoshop so we can examine the RGB and alpha channels, because the alpha channel and the way it's authored is pivotal to this effect working. It's how we get just little bits of blood to show up at different times as the player becomes more damaged. So I'm going to open up Photoshop and I'm going to load in this texture that I'm using here called My Blood Texture, which is this texture here. It doesn't look particularly exciting when we see it in Unity, but let's load it into Photoshop and we'll have a look at the alpha channel as well. So here I am in Photoshop, and what you're looking at is the RGB channels of our blood texture. Now, if your interface looks very different to mine, you're probably using a much newer version of Photoshop than me. I'm actually using Photoshop CS4, believe it or not. I like to work under the adage that if something isn't broken, don't fix it, and this is still doing everything I want it to do, so I don't upgrade until I absolutely need to. Okay, so as you can see, the RGB channel just contains a big square of red. Now I'm using some different shades of red in there, although it's not necessary. The blood effect will still look quite good if you just made the RGB channel a single block of red, all of the same shade. But as we blend the blood pixels with the frame buffer pixels in our shader, I think it makes it look a little bit nicer if not all of the blood is exactly the same color. The alpha channel, however, is much more interesting as it controls when and where these blood pixels are allowed through the filter and to be blended with our frame buffer. So let me enable the alpha channel and turn off the RGB channel so we can just see the alpha image. And as you can see, we have lots of different splats of blood that I really just placed quite randomly, but some of them are very intense and near white, and some of them are much more dull. Now, the way this technique works is we have like a threshold value. So imagine we have a value that can be set in the range of 0 to 1, where if that threshold value is set to 1, it means we have 100% health. And if it's 0, then it means, well, we're dead basically. It never gets down to 0. And the way this threshold works, as our health declines from 100% down to 0, this threshold value will move down from 1 to 0. And in our image effect shader, this shader is always going to be saying, I'm only going to process and let through the pixels in our blood texture that have an alpha value that is greater or equal to the threshold. So if our health was at 80%, for example, our threshold would be 0.8, and only pixels in our blood texture that have an alpha value that is more intense than 0.8 will actually be selected from the texture and blended with the frame buffer. So if we imagine that a threshold of 0.8 is currently being used, all of this blood here where it's all pretty dull is not going to be sampled. It's going to be filtered out. But these white pixels and all these little specks in the middle here, and some of these brighter pixels down in the bottom left corner here, and these over on the right, they will pass the 0.8 threshold intensity mark, so they will be allowed through. So at the 0.8, we would see a screen where only this blood gets shown here in the middle, and a little bit around the outside. Now, as the threshold drops in response to our health continually dropping, we start letting through a larger range of alpha values. So we would then start to see some of these duller pixels allowed through as well. And you'll see later on that we don't just do that, we also boost it a little bit as well, so that it's even possible when we're fully damaged for even these black pixels to tint the frame buffer red. So that's basically what the image looks like. Let's see now how I created it. So I'm going to go to the File menu, I'm going to choose New, so I'm going to create a new image. I'm going to make it 1920 wide by 1080 high. It doesn't need to be. This could be 256 by 256 if you wanted to. It doesn't even matter if it matches the aspect ratio of the display mode, quite honestly. I've tried it with square textures as well. And even though they technically get stretched, with an effect like this, it doesn't really show, and sometimes it can actually look quite cool. Mess around with the different texture sizes to see what suits you, but I'm going to put it in 1920 by 1080 for now, just because that's my monitor screen, and I think that will look nice in the video. I'm going to create this with a transparent background, and I'm going to click OK. And then the first thing I'm going to do is, you can see it's created a image with me with a single transparent layer. I'm going to color that layer completely black. So I'm going to make sure I have the black color selected. And I'm going to choose my brush tool. And I'm just going to put on a really big brush like that. So I just very quickly make it all black. But because I've made that a black layer, it means I can go over to the layers window and I can turn that layer off when I want. Now, at the moment, this image hasn't got an alpha channel. I'm going to add that later. So I'm just working in the RGB channel, which you saw a moment ago will eventually end up all being red. However, it's not nice, especially in Photoshop, working and drawing in the alpha channel directly. So what I'm going to do is create the alpha channel as a colored image first of all, so I can see the intensities of the blood I'm using, and I'm going to use that to paint a colored version, if you like, of what we want the alpha channel to be. And the reason I use a black background is because it's actually easier to see how it's going to look in the actual scene, because in the game the frame buffer is always going to be quite dark, or at least nearer black than it would be white. So it gives a more truer impression of what the blood is going to look like when it blends with a real scene. And then what I'm going to do is I'm copy that image, convert it into grayscale into the alpha channel. But I'll also keep a copy of the grayscale image in the RGB channel on a layer that I can just turn off. And then what I've really got is the basis for my normal map as well. What we're doing at the moment is painting essentially the normal map and the alpha map, even though I'm really doing it in the RGB channels to begin with. And then once we've got the pattern of the blood in the alpha channel, and I've made a backup of what that looks like in the RGB channel, so that I can turn that layer on and off when I wish to export my normal map, I'm then finally going to just sort of paint lots of red in the RGB channel so we get that big red block. So how do we create blood in Photoshop? Well, I'll tell you the way I did it. There's two ways you can do it, but I'll tell you the way I did it. One way you could do it is you could just go to Google Images, and you could type in something like blood splat texture, something like that, and go to Google Images, and you can see that there's lots of sort of different blood splats that you could use. Now, some of these are on a white background, which would be no good for you. The ones that are on a black background are fine. So you could use this one here and this one here. And to help you in your search, you could also go to settings, not settings, go to tools. That's the one. And for color, you could do transparent. And then that will only give you blood splats that have a transparent background on them. So you can drag them in, resize them, position them around the canvas to get lots of nice realistic looking blood effects. And in my texture, I actually did a little bit of both. I mostly did it with Photoshop brushes, and then I brought in a few of these blood splats for some of the detail in the middle. In fact, I think that might actually be one of the ones I used there. But what I'm going to do for this tutorial is I'm just going to use the brushes in Photoshop. Now, Photoshop by default doesn't have any blood splat brushes. So we're going to need to download some brushes and install them in Photoshop. So I found this website here. Now I'm going to zoom in here on the address bar so you can see the address. It's anfrost-art.deviantart/blood-splatter-art/1053182115. So you might want to pause the video and take a note of that. And on this page is a collection of blood brushes, 16 in all, that have been authored by Anne Frost, and she is good enough to give them to us completely free of charge. So download this by going over onto the right hand side here. Of course, by the time you watch this video, this website UI may have changed a little bit, but at the moment you can see I have this little download link over here, and that's going to download a 2.1 megabyte file in ABR format. And ABR is the format of brushes in Photoshop. So if I close this window down and minimize, or at least unmaximize, my Photoshop window, excuse my desktop background, that's me there singing on stage. I also do a bit of singing. I tour with a band that does a tribute to the Bee Gees, a theatre show, believe it or not. So I can hear you laughing now. Stop it. Okay, so where did I download that file to? Okay, so here it is. So in order to install these brushes, all you have to do is just drag and drop them into your image like so. And then if I select my paintbrush, it's still here, and open up the brushes drop down, you can see all the regular brushes there, but as I start to scroll down, hey, look at that, I start to see the actual blood brushes. If I make them a bit bigger, you can see what they look like. So there you go, you're starting to see what they look like now. And let me undo all that because I don't want all of those. And so that's all there is to it. Just download that ABR file, drag and drop it into your Photoshop project. Now, I don't want to draw the blood directly onto this black background layer, which will happen at the moment if I do that. So I'm going to create a new layer and draw my blood on there. So I go to the layers menu, I choose new layer, and I'll call this the blood layer. And what I'm going to do is I'm just going to very, very briefly mock up what I did. I obviously spent quite a bit of time doing my texture, and I don't want to waste your time with exactly how I did it. So I'm just going to show you the basic technique, but I'm probably going to create a pretty crappy looking texture just due to the speed at which I'm going to go through this. So I'm going to create some dark blood to begin with. So this is going to be sort of the blood that doesn't show up straight away, and I'm going to choose a nice blood texture from those blood splats that I installed. And I'm going to, that looks a pretty good size. And I'm going to consistently kind of change the size of the brush quite a bit so I don't always get all my stuff looking the same. Put some of that in there like that, like that. You get the idea, right? I'm just kind of creating stuff, and then I'm going to go to different brushes, choose different, and I should probably also just create this at a, actually I'll make this one a bit darker, I think, because I think that first one might have been a little bit too light. And I'm changing the size a little bit now so I can put some little specks in like that. I mean, obviously, because I'm not spending too much time over it, it's looking a little bit, you know, you can see quite a few patterns here. That's quite a good one, isn't it? Yeah. Let me turn that down a little bit in size. And what I'm going to do is I'm going to put in some lighter specks now. So these are ones that are going to show up quite early on, you know. So you don't want too many of them. Let's have a look at some of these other brushes. I wish the brush window was a little bit more detailed. So even when you make the window bigger, the brushes don't actually get any bigger, do they? Okay, let's see what I've got here. Got some here, they're pretty sort of weird, drippy looking brushes. And what we'll do is we'll go to some small brushes and we'll put in some finer detail in different sizes and different shapes. Like so. And then what we'll do is put some nice bright ones in. Probably not that big, just a few little speckles here and there. I want something that's a little bit more spaced out. Something like that, maybe. Okay, so let's just go with that for our blood texture for now. In order to create this in the alpha channel, I'm first of all going to need an alpha channel. So I can do that in Photoshop by going to my channels window here. Now, if it's not selected, make sure you select it to give it focus. And if you're not seeing a channel window at all, then just go to the Windows menu and make sure that channels is ticked, and then it will show up. Once you've got the channels window up, what you want to do is you want to go to this little new document icon down there, and that's going to create a new channel for you. And you can see by default it's called Alpha 1, and as you can see there is literally nothing in it at the moment. It's purely black. What we want to do now is we want to grayscale this image, and then we want to copy that image into the alpha channel. So the first thing I'm going to do is I'm going to, with my blood layer selected, and I've still selected the RGB channels here, not the alpha channel. I'm going to go to the image menu, I'm going to go to the adjustment sub menu, and I'm going to choose black and white, like so. Doesn't look too bad, but at the moment I don't really like the contrast of it. There's not really a big enough range between the brightest pixels and the darkest pixels. So what I generally tend to do with things like that is I go to the curves and I sort of boost up the top end like so, and then sort of boost down sort of like the low end like so. So we've got a much, I'm doing this very quickly guys, but you get the idea, right? So I'm making the duller pixels a bit duller, and I'm making the whiter pixels a bit whiter. So now that I have these two layers, remember I have two layers in my RGB channel at the moment, just the black background layer, which if I turn off, I'm just left with that. Now you can see why I didn't author it on a transparent background, because it's very hard to see the intensities. And I have obviously my blood layer. So what I'm going to do is I'm now going to collapse those two layers down by selecting them both in the layers window. Once again, if the layers window is not open to you, then just go to the Windows menu and choose to make the layers window visible. Then I'm going to right click with both of those layers selected, and I'm going to choose merge layers like so. And then what I'm going to do is go to the select menu, choose select all, okay, and then I'm going to do copy. So I've now copied this to the clipboard. Now what I'm going to do is I'm going to turn off the RGB channels and go down to the alpha channel, and I'm going to paste what I just copied to the clipboard directly into there, and we now have an exact copy of what we just created in the RGB channels in our alpha channel. Great thing about it, we don't need, if I turn off the alpha channel in a minute, we don't need this layer now in the RGB channel, but I can keep this layer hanging around, because later on when we want to create a normal map for it, well, there's our grayscale normal map as well, which we can just export as a JPEG. But for now, I'm going to turn off my my blood layer in the RGB channel, and all I have is I have nothing in the RGB channel, and I have the blood splat in the alpha channel. So all I need to do now is I need to fill this thing up with lots of different shades of red, once again using the blood brushes. So I'm going to go to my brush tool again. This time I'm just going to choose a red color like so. Give myself a great big brush. Oh, I need to create a new layer, of course. There's nothing to draw onto at the moment. So I will call this the I'm going to call this the RGB layer. This is the layer that we're actually going to use to contain all of our RGB stuff, and I'll just put like a load of stuff like that in there at the moment. In fact, I'll fill it all in red at the moment like so, and then what I'll do is I will go to a different color like so. I'll go to a different brush I think as well, something like that. Go to a different color again. Don't want to go to that color, do I? Remember, the actual pattern of this isn't really that important. We're just trying to create some nice different shades of red so that any of these pixels that are allowed through the filter defined by the alpha mask won't all be the same color. So let me go to another brush. Scale this one down quite a bit, not that much. Don't want to scale it down that much, do I? I'm covering over quite a lot of this actually, because I realised that I think I made the one underneath it, the real bright red. It's too red. Don't want it to end up looking like Crayola. And we'll put some red shades in there as well. And oh dear. Not a big fan of that. I'll put some of that in there as well. Okay, so you get the idea. And I think what I'll do with that is I will also put a curve on that as well, make it a little bit darker. And maybe bring down the top end. Actually, I'll put that up, but I'll leave the top end down like so. Okay, so I think that will do for this demonstration. We're not really going to use this texture. We're going to use the one that I created earlier. Because this was done in such a hurry. The main idea of this is to show you how to create it, how to save it off and stuff. So once I had this texture with its RGB channel and its alpha channel, I make sure that they're all enabled, and then I save it off. And what I want to do is I want to do save as, and I chose to save it as a TGA, okay, because that allows support for alpha channels as well. Make sure you have the alpha channel box highlighted there, okay, very important. And choose 32 bits per pixel. That's so that the alpha channel gets saved off as well, and everything is in nice precision. So at this point, I now had my blood texture that is going to be used for the basic operation of drawing the blood to the screen, complete with its alpha channel. The next thing I needed was a bump map. So I already had that prepared, but what I want to do is I want to turn off the alpha channel so we can see what it looks like in the RGB channel, turn off my RGB layer and re-enable that blood layer. Now I think, to be honest, I made a bit of a mistake here. Did I? No, I didn't. No, I didn't. I think what I will do for the bump map is I will add another curves to it again and just give it a little bit of a boost so that the bumps are really kind of emphasized. And then what I'll do is I don't really have to worry about the fact that this has got an alpha channel, because I'm going to save this now off as a JPEG, which is going to flatten the image. So when I save it off as a JPEG, the unused RGB layer will be thrown away, and so too will the alpha channel. So I do that by going to save as, and then I go to TGA. No, I don't have to go to TGA. I can go to JPEG, sorry. And then I would just save that as, say, something like blood normal, and choose to save it at the highest detail. Okay, so put it on large file, click OK, and then what you'll have is you'll have your blood texture and its normal map ready to be imported into the project. You can see that mine are here. Here is my blood texture. So I just dragged and dropped both of these into my project in Dead Earth. So there's my blood texture and there's my blood normal map. We'll do that now in our project. We'll drag these things in so that they're ready to use. So I'm going to switch now over from my production version of Dead Earth over to our student prototype. And what I'm going to do while I'm working on this is I'm going to, I think, turn off the lighting in the game view. Well, not turn off the lighting, but bring the lighting up a little bit so that we can see what we're doing, because we made it very dark, didn't we? So I'm just going to bring the ambient intensity up quite a bit for now, just so we can see what's going on. I've taken it up from 0.66 to 1.44. So then what I'm going to do is in my textures folder, I'm going to copy in our blood texture for our camera effect. As you can see, it's called my blood texture. And I'm also going to copy in the normal map to go along with it. There it is. I'd lost it for a minute. There you go. So let's select our normal map first of all, and make sure you have the inspector enabled, because we need to set the import settings for it. And the first thing we need to do is tell Unity that this texture is a normal map, and we'll put the bumpiness down to something like that to begin with. We'll tell it we want a nice smooth normal map, and we tick that tick box that says create from grayscale, because remember, this isn't actually a normal map, it's really a height map. Because it's a grayscale image, so Unity can now use that to create a normal map from. So if I press apply, let's see what that looks like. It might still be a bit noisy. I'll leave it like that for now. We might want to just reduce the strength of the bumpiness. With the blood texture, what we need to do, I don't think we need to do anything with the blood texture, do we? Okay, so I think our textures have been imported correctly. So now we need to talk about image effects and how we write them. Oh, and before I forget, I should have mentioned this just now. These two textures here that we're using in this lesson, you can download those from the website. They will be in a zip file that accompanies this lesson, or alternatively, you will also find a link to that zip file in the resources section of the Dead Earth channel. So what we're going to do in a moment is we're going to create the mono behavior image effect script. That's the script that is going to manage the amount of blood that needs to be shown on the screen, and is also going to be responsible for sending the current blood amount into the shader that we're going to develop. and that's the script that we're going to add to our camera. And we're also going to develop the image effect shader itself, and we're going to develop these in tandem because they're codependent. So in order to see if one is working, we also want to kind of create the other one at the same time. Okay then, so unless you have been living all alone on a desert island for the past 25 years, I am sure you have heard the term shader being used with respect to 3D graphics. Even if you're not an experienced shader programmer, you probably know that there are different types of shaders. Vertex shaders, pixel shaders, and more recently, compute shaders, which all help in some way to produce the final image that we see when playing a game. In order to be a competent shader writer, you really need to have a good understanding of the 3D mathematics involved in a 3D game engine such as Unity. Unfortunately, there isn't really any quick way around this. You need to understand in depth how the models that we create in modeling packages such as 3ds Max, Maya or Blender, and that we then import into Unity, are really just 3D mathematical representations of objects, a series of points called vertices, defined in 3D space, which when connected with other vertices define the outer skin or hull of our objects. These vertices define not only a position, but also contain other bits of useful information as well, such as color or texture coordinates. These will later help the engine know what texture and colors to use when rendering the object's surface. But of course, when we import these 3D mathematical representations of our objects into Unity, they are not in a form yet of something that can be rendered. Even after we have positioned all of these objects into the scene, the game world is still just a mathematical 3D representation at this point. Now, our monitor screen is two-dimensional, and thus, after assigning world positions to all our objects, every single frame, the game engine has to take all of these objects in the scene and project them into a 2D image that can be displayed. Along the way, lighting calculations are also performed to factor in any lights that we may have placed in the scene and unseen geometry clipped away so that it isn't needlessly processed. When we write vertex and or pixel shaders, we are essentially taking over part of that process ourselves and become responsible for implementing the code that does much of these tasks. Therefore, we need quite intimate knowledge of the 3D math involved in transformation and lighting. So if you don't understand what 3D transformations are, or if you don't understand what the world matrix is, or how the projection matrix works, or if you don't know what homogeneous clip space is, or what UV coordinates are, and what triangle interpolation is, sorry, you're just not ready yet to write your own vertex and pixel shaders. However, many years ago, I developed a DirectX 9 course for the Game Institute, and it's still available on the website today, and I think it's just what you need to bring you up to speed mathematically in these areas. Although it was written for the DirectX 9 API, which of course is now mainly obsolete, most of the material is pretty API agnostic and covers in detail how 3D models get transformed into a 2D image, and how lighting calculations work, and also it's a good introduction to shader programming techniques. Things are not quite so bad for us in this lesson, however, as we are only going to be writing an image effect shader, which means we aren't really concerned with doing any lighting calculations and things like that. But I'm sure later on in the development of Dead Earth, we will want to create some custom shaders for our objects, so you might as well jump into the material now and have a read. Otherwise, you're going to find yourself left behind here. Let me show you where that material can be found on the website. So here I am on the Game Institute website. I've logged in. I'm currently looking at the dashboard. Now your UI may look a little bit different to mine because you may not be subscribed to all the channels that I'm subscribed to. And also as an instructor here, there may be things that you only get if you're a teacher. But basically, you just need to go to the site channels and you need to go to the catalog, and that will show you all of the categories of courses that we offer. And if you go into the programming category, you can see there is this course here called Graphics Framework Programming, and it says DirectX 9 in parentheses. Click on that and choose to join the channel. And there you go, you're logged in. Now this has a series of lectures, but it also has a really big textbook, 2 textbooks I think, that go into a lot more detail as well. So there's lots of stuff here. Now you don't need to see all of this. So I'm going to point out the lessons that I think are relevant and the ones that don't focus on DirectX 9 stuff. The first 2 lessons are really important. They describe basically how 3D points are transformed into a 2D image. So That's pretty cool. It doesn't cover anything like lighting or anything like that yet, but just the basic matrix math involved, and you'll learn what a world matrix is, what world space is, what object space is, and things like that. So 1 and 2 are definitely worth looking at. Also, lessons 7 and 8 are very important. Lesson 7 describes in detail things such as the projection matrix, how clipping is performed, and what the view matrix is, and how it's used to simulate the presence of a camera in our scene. The view matrix is what allows us to walk around the scene, and it's what allows us in Unity to pretend that there is this high-level concept called a camera, when really, of course, it's just a matrix that is applied to all of the vertices in our scene to transform and move the world around to simulate the player moving around the world. Number 8 is pretty important too. It actually describes the DirectX 9 lighting pipeline and what lights are available, but these are very similar, almost identical to the main light types that are used in Unity. Point lights, directional lights, spotlights, things like that, and describes how their lighting calculations are performed. Now, of course, this is really important if you're going to write your own shaders later on and do your own lighting calculations. 9 and 10 are also worth a look at. It describes how texture mapping works and how triangular interpolation works. Very important stuff to know if you're going to be writing your own shaders later on. And this also applies if you're going to be writing your own surface shaders as well, which is a more of a high level shader framework that Unity provides shader developers with. But we'll get into more on that later on. And then, so what have we got so far? We've got 1 and 2. Want to see those lessons. We've also got 7, 8, 9 and 10. Definitely worth a look. Also, number 11 is pretty useful. Describes how transparency and fog works. Basically, they're kind of two sides of the same coin, really, as fog is kind of implemented in the same way as transparency. And then if we scroll right down to the bottom here, you can also see that we have 2 lessons on effect files and shaders, which is a good introduction to shaders and definitely worth a read before you really carry on with this lesson. Now, these are lectures that you can actually download. They're just PowerPoint presentations. This was done quite a long time ago, but they're very useful. And if you go to resources as well, what you'll also see under textbooks is we have the GP1 textbook and the GP2 textbook. These are PDFs with really detailed information, much more detailed than the lectures. So I would recommend that you read both of the textbooks and watch the lectures. Once again, with the lectures, they have the same chapter assignments as the textbooks. So the same chapters that I told you to read also apply to the textbook as well. Okay, so do check that out and make sure you subscribe to the Graphics Framework Programming in DirectX 9 channel. Now, from this point on, when I'm talking about shaders, shader inputs, shader semantics, and homogeneous clip space, I'm going to assume that you know what these things are and that you've read this material, okay? Unity allows us to create our own vertex and pixel shaders so that we can implement any lighting model that we choose, and so that we have total control over how each pixel on the screen is colored. We write shader programs using a language called HLSL, short for High Level Shader Language, or sometimes referred to as CG, short for C for graphics. Although HLSL and CG have distinct and different origins, for all practical purposes, we can think of them as being the same thing when developing shaders in Unity. You may also hear vertex and pixel shaders being called slightly different things, such as vertex programs and pixel programs, for example. And Unity's own documentation refers to pixel shaders as being fragment programs, or fragment shaders. More recently, the term fragment is the preferred term because shader usage has many more applications these days than they used to. A fragment shader, for example, may be used to render to a texture, where it is actually computing the color of texels in a texture, rather than pixels on a screen. And furthermore, just because a fragment shader is executed doesn't necessarily mean that it's going to output anything, such as the case when using a fragment shader to clip pixels out of an image. Therefore, the term fragment shader more generically describes the fact that it is a function to compute some output color, which may ultimately be used in a variety of different ways, not just for coloring pixels. Writing our own vertex and fragment shaders in a way that integrates with an engine such as Unity and its game world is actually quite challenging. We need to implement the entire lighting model, and we need to know if a surface has to be rendered multiple times and color blended to achieve its final result. Such a technique is referred to as multiple pass rendering. Furthermore, we need to be aware of where the lights are in the scene and of the various global lighting and fog settings that may currently be in use by the engine, so that our shader reacts to light and fog in the same way as the built-in shaders. We want a consistently lit scene. Furthermore, we need to figure out which lights affect which surfaces, how they are attenuated with distance, and a million other things besides. To make writing shaders easier, Unity Technologies introduced a higher level framework that does much of this heavy lifting for us. They called it surface shaders. Surface shaders are not some magical new type of shader. In fact, surface shaders are compiled behind the scenes into standard vertex and fragment shaders. But they allow us to write our shader in a way that removes the burdens of lighting from us. In surface shaders, we simply specify how our fragment should react to light, its material properties if you will, and then output those properties. When the surface shader is compiled into a fragment shader, those material properties will have been automatically pushed through the lighting, fog and shadow functions used by the rest of the engine. Therefore, when writing more generic shaders for use by the objects in your scene and their materials, you're probably always going to find yourself writing surface shaders. However, you can ignore surface shaders completely if you want to, and write all of your own vertex and fragment shaders from scratch. But like I said, in the more general case, it doesn't make a lot of sense unless there is some really specific functionality that you want to implement that just cannot be implemented using the surface shaders framework. However, image effect shaders are very different. These are not shaders that are used by the objects in our world. They are shaders that are used to simply modify the image in the frame buffer after the scene has been rendered by the camera, and are therefore always implemented as just standard vertex and fragment shaders. In fact, you will see later how behind the scenes image effects are implemented by essentially drawing a large quad over the 2D image of the scene that currently exists either in the frame buffer or the render texture. As the quad covers the whole screen, when this quad is drawn, it will call the fragment shader function for every single pixel in the image. Now, as input into that fragment shader, Unity will provide us with the input texture that contains the current image that is in the frame buffer or render texture, which means for each invocation of the fragment shader, we can sample the color currently at that pixel, which will include any modifications made to it by other image effects executed higher up the effect chain, and can then modify that color in some way before outputting that modified result from the fragment shader and onto the rest of the image effect chain. So just to be absolutely clear here, when we implement an image effect, we are really just drawing a big quad over the entire screen so that the fragment shader function gets called for every single pixel. Okay, enough talk. Let's create these scripts. So I'm going to go to my scripts folder and I'm going to create a new folder inside my scripts folder, and I'm going to call this image effects. This will contain all of the image effects that I'm going to create rather than those provided by Unity that will be in the standard assets folder. Inside the image effects folder, if I drill down into there, I'm now going to create a new C# script, and I'm going to call this camera blood effect, like so. I'm now going to select my camera in the scene, which you will remember is under our FPS controller container object, and we have a child there called FPS camera, and I'm going to drag that onto my camera, and that is going to be the first image effect in our camera's image effect chain. So that's the mono behavior. That's the script that's going to be responsible for keeping track of the current threshold value that we're going to use for making the blood either appear or disappear. And it's going to be responsible each update for sending the most up-to-date information into the shader so that the shader can do its thing. But we're also going to need to create a brand new shader as well. So where should we put this? Well, we don't have a shaders folder at the moment. So what I'm going to do is directly under my Dead Earth folder, I'm going to create a new folder and I'm going to call that shaders. I mean, you could choose to put your shaders in your scripts folder because shaders are a type of script, but I like to keep them separate because scripts to me means mono behaviors in Unity and shaders are something completely different. So I'm going to drill down into my shaders folder. I'm going to right click, I'm going to choose create, and then you'll see that there is a shader submenu. And we have 4 choices, at least in this version of Unity we do, there may be more now. But what I want to create is an image effect shader. Now the only difference between which one of these we choose is really just the default code that Unity will put in that shader. You can see we have a standard surface shader there. So if you want to see what a surface shader looks like, doing something pretty basic, then create a new surface shader and have a look at it, or an unlit shader, or a compute shader, which is something completely different. What we want is an image effect shader, which basically means it's going to create a new shader with the basic stub of a vertex shader and a fragment shader that we can then modify to fit our own purposes. So I'm going to create a new image effect shader, and I'm going to call this camera blood effect, but I'm going to spell it right, like so. So we now have our new shader. Now what I'm going to do is I'm going to create, just for temporary purposes while I'm explaining how shaders work to you, I'm going to create a material. I'm just going to create that in the Dead Earth folder because I want it somewhere. I don't want to put it in my materials folder because I'll forget and I'll leave it there. And this is something I'm going to want to delete straight away after I've explained to you how Shader Lab and properties work in shader declarations. So I'm going to create a brand new material, and I'm just going to call this my temp shader material. Okay, so there we go. Now we have everything we need, I think, for me to start building and explaining our image effect script and shader. So let's start by drilling down into our shaders folder, and let's open up the camera blood effect shader in MonoDevelop so we can see the basic boilerplate code that Unity has provided us with as a base to start coding our shader from. So here we are in MonoDevelop, and what we're looking at here is the code that Unity created for us automatically when we told it we wanted to create a new image effect shader. Although the code here is quite small, it's actually a fully functional shader that simply inverts the color of the input texture, whether that be the current render texture or the frame buffer. And so in other words, black becomes white, white becomes black, etc. Now we're going to talk about what all of this stuff means in a moment and what all these keywords do. But for now, I just want to sort of zoom in and focus on the section of this shader that is in between the C program and the end CG marker, because it's between the CG program and the end CG marker that we actually put our high level shader language code, the code to our actual shader, if you like. And it looks very much like any other C-like language. You can see that we have structure declarations here. We have a variable declaration here of a sampler 2D. And we also have two functions here, one called vert, which is our vertex shader, and another one here called frag, which is our fragment shader. So a shader is really just a function that the Unity pipeline is going to call when it needs to either transform a vertex from object space into homogeneous clip space, or in the case of a fragment shader, when it needs to calculate the color for a pixel or texel in a render texture. And high-level shader language is also very flexible, so we can, for example, call our vertex and fragment shader functions whatever we like, and those functions themselves can call other functions that we may have also defined either in the CG program block or in an external file, and we've brought in via an include directive. So let's sort of have a little look through this code and just explain what we're looking at here. So underneath the CG program directive there, you can see that the first thing we have is a keyword that has a pound sign followed by pragma. And this is our way of specifying to the shader compiler certain things that we want it to be aware of as the compilation is taking place. And there's several pragma directives, and you can look them up in the Unity documentation. And we're using two here. And the two that we are using allows us to tell the shader compiler which function we wish to use for the vertex shader and which function we wish to use for the fragment shader. Because although we've just got one fragment shader and one vertex shader function in this particular code, more complex shaders may have large functions and call into multiple other functions as well. So if we've got lots of different helper functions defined in the shader, Unity needs to know which one is the actual function, the parent function, that it's going to call when transforming vertices or coloring pixels. So we do that by saying pound pragma and use the vertex keyword, which tells Unity that we are now setting what we wish it to consider the vertex shader, and we tell it we wish it to use a function called vert, which is this function here. So when our objects are being transformed from object space into homogeneous clip space, for every vertex that's processed by the pipeline, Unity knows that if it's using this shader, this is the function that it needs to call, and it's going to pass in all of the input data that this shader needs to know about that vertex. And we'll talk a little bit about the input data to a vertex shader in a moment. Next up, underneath the Pragma Vertex directive, you can see we have a similar thing again, where this time we use the Pragma Fragment directive to make the shader compiler aware of the function that is our fragment shader's top level function. So in this particular case, we're telling it that there should be a function defined called frag, and this is the function that the pipeline should call when it's processing each pixel in the image to which this shader is applied. Nice thing about this is because we are telling the compiler via these Pragma directives what the names of these functions are, it means we can call these functions whatever we want. They needn't be called vert or frag, they can be called whatever we like. Also, outside of the vertex and fragment shader functions, you can see we have other things that we would expect to see in any high-level language. For example, here you can see there's a variable defined that is of type sampler2D. Now we're going to talk about what all of these different variable types are in HLSL in a moment, but sampler2D is basically high-level shader language's way of defining a 2D texture, and this variable is called main text. So in our fragment shader, whenever we wish to sample colors from that texture, we can use the main text variable to do it. Now don't worry if you don't understand what any of this means yet, or how, for example, that main text variable is used. We're going to drill down on the specifics in a moment, I promise. For now, we're just trying to get a general feel for how the shader is laid out and really just make ourselves feel comfortable that HLSL doesn't really look that much different from code that we would write in C# or C++. So underneath the Pragma directives, where we set the vertex and fragment shader functions for the compiler, you can see we have this #include directive. And if you've done any programming in C or C++, you'll be immediately familiar with what a #include directive does. Often, when we're writing shaders, if they're complex shaders, they will often need to perform many tasks and call lots of different helper functions, so that the general task of the shader is broken down into lots of little subtasks. And often, the functions that we write, which may be as simple as just how to transform a normal of an object from object space into homogeneous clip space, for example, are often functions that we wish to reuse over and over again in all of our shaders. And rather than have to write that code over and over again, or have to copy and paste the code in every time we wish to reuse it, what we can do is we can save it in what's called a CG include file, and that's a file with the .cginc extension. And when we do that, we can use the #include directive to bring that file into the shader that we're currently writing. It just contains high-level shader language code. Often it will be variable declarations, macros, or other functions that we wish to reuse in our other shaders. When we use the #include directive, what the compiler will do when it encounters it is it will open up that file that we specify, it will pull all the code out, and it will directly insert it into our shader code just prior to the shader being compiled. So it's as if we rewrote all that code again, and our shader will have access to all the variables, macros, and functions defined in that CG include file. The file that's being included here, which is included by default when we create a new image effect in Unity, is called unitycg.cginc. Now this is a file that is provided by Unity because it contains lots of helper functions that are useful when writing your own vertex and fragment shaders. Now you can of course create your own CG include files. If you create some really reusable functions, then by all means put them in include files, and then you can include those files in all of the shaders that you write so that they can all access that functionality. But if you want to have a look at the CG include files that are provided by Unity Technologies, you can actually do that. The source files install in the Unity Editor's installation folder, and I would certainly recommend checking them out. There's a lot of include files there. There's literally thousands of lines of HLSL code that has been written by the folks at Unity Technology, so there's a lot to be learned from going through them. You want to know what functions are available anyway, so that you don't bother sort of writing your own functions when you find that Unity provided you with functions that already exist. And furthermore, if you use the functions that are supplied by Unity Technologies, because they know their engine really well and have tested all of the different problems on different platforms, a lot of their functions have preprocessor directives in them so that the code compiles differently and more efficiently for each platform. So definitely worth having a look. So where are they? Well, let me call up my file explorer. If you drill down into your C drive, then into your Windows Program Files folder. Now, I'm programming on Windows 10 at the moment, so you'll have to look in the documentation to see where it is on a Mac or Linux. And you drill down into your Unity installation folder, and you can see there's an editor and a mono develop folder. Drill down into the editor folder, and you'll see there's a folder called data, Drill down into the data folder and you will see there is a folder called CG Includes, which contains many files. These are all the CG Include files that Unity have written for us automatically. Now, some of them are just to do with things like terrain or vegetation. But that's pretty important, because if you want to write your own replacement terrain shader, then you're probably going to want to bring in, Terrain Engine CG Ink into your shader so that you have access to all of the functionality that Unity's built-in terrain shaders use. There'll be lots of functions there to deal with, animating trees and grass and billboards and stuff like that. If you look here, you can see that here is the CG Include file that we're including. If I call up the Include Files documentation, if you go to the Unity documentation, drill down into the graphics reference, the shader reference, the writing, vertex and fragment shaders sub-reference, and then call up the page called built-in shader include files, you can see it lists some of the important ones here and tells you how they're used or where they should be used. So you can see, for example, terrainengine.cginc contain lots of helper functions if you wish to write your own terrain and vegetation shaders and need access to the engine's terrain and vegetation information. Here is Unity CG.inc, the one we're including, and it just says it contains commonly used helper functions. You'll see that there's functions in there, for example, to convert a vertex from object space into a homogeneous clip space. You can also see that there are two other include files here called HLSL support.cginc and Unity shader variables.cginc that we don't have to bother including in our shaders because they are automatically included. And in the case of Unity shader variables.cginc, they contain all of the variables that allow our shader to get access to information about the engine and the object being rendered. So if we were rendering an object, for example, it would allow us access to things like the view matrix, the object's world matrix, things like the projection matrix, and things like that. The HLSL support.cginc include file just contains lots of helpers and macros that we might use to extract information from an engine in a way that makes it cross-platform friendly. An example of that might be when we wish to extract a normal from a normal map. There's a macro or a function that should be called to do that so that it caters for the fact that on different platforms the normal may actually be encoded differently in the normal map texture. So we'll see some of this stuff being used a little bit later on. So let's open up unitycg.cginc, which is the file we're currently including in our shader, and you'll see what I mean. It contains many sort of helper functions that we may want to call from our shader if we wish to do certain things. So there's one here called Unity World Space Viewdir, and we could call this from our vertex shader, pass in the object space position of the vertex currently being transformed, and what it would do is it would calculate the world space direction vector from the camera to this vertex position. And you can see there's other flavors of this like the world space viewdir, object space viewdir, etc. Let me scroll down and show you some other examples of things. You can see we have a function here called luminance, which is a function that we can call if we wish to calculate the luminance of a pixel in a fragment shader. Doesn't really matter how it works. Fact of the matter is, if we wanted to create a black and white image effect, we could create a fragment shader that simply samples the input texture, sends the color into this luminance function, and it would get back the correct monochrome color that we could then output from that fragment shader. So lots of stuff in there worth having a look at, and you'll see us using some of these functions as we start creating our own blood effect shader. Okay, so next up you can see that we're declaring some structures here, and these structures are used to define the input and output data to and from the vertex shader and the fragment shader. So let's talk a little bit about the variable types that we can use to represent numbers in HLSL, and also talk a little bit about what these weird semantics are at the end of our variable declarations when declaring these structures. So let's talk first of all about how our shaders get supplied data from the Unity game engine so that they can accomplish their task. We'll concentrate first of all on the vertex shader. Now, when a 3D scene is rendered, every frame, all of the vertices of the objects have to be transformed from their object space representations, as defined in a modeling program, into homogeneous clip space. Now, once they are in clip space, the engine can then perform the clipping process on that object's vertices and later perform that homogeneous divide by W to project the object's vertices into two-dimensional normalized client coordinates. The task of transforming a vertex position from object space into clip space is that of the vertex shader. For each vertex of a model, the vertex shader will be invoked by the game engine and supplied with the object space position of the vertex. A vertex shader will most commonly, at least, have the task of multiplying that object space position by the object's world matrix, the camera's view matrix, and the projection matrix to calculate its clip space position, which can then be output from the vertex shader and fed back into the game engine's rendering pipeline. More commonly though, vertices will contain a lot of other information than just the object space position. A textured object will commonly store at least one, but maybe more, sets of texture coordinates at the vertices. Vertices will often contain object space normals or tangent vectors for use in per pixel lighting. Skinned meshes, for example, will contain per vertex blend weights and bone indices, while some models will even store colors at the vertices. How much of this data is available and how much of it we wish to use is down to the shader's input structure. The point here though is that vertices can come in all sorts of shapes and sizes, and shaders may want to use or not use all of the data that is available. We need a way of defining the input parameters to our shader functions such that we can be flexible and tell Unity only the data that we want and in which parameters that data should be loaded into. Furthermore, because the data stored in the vertices is interpolated across the surface during triangle rasterization, we may also want to perform some calculations in the vertex shader itself and store the result of those calculations in the vertex shader's output structure so that it is interpolated across the surface and accessible per pixel in the fragment shader. There are typically many less vertices in a model than pixels used when rendering it, so it often makes sense to move some of the math from the fragment shader into the vertex shader to lower the rendering computation overhead. Now, an HLSL vertex shader can take as input a varying number of parameters which are marked with semantics to inform the engine which parameters should receive which piece of information about the vertex. This is how Unity knows in which of your parameter variables to store the bits of information of the vertex. Furthermore, because we can have a large number of inputs into a vertex shader, and because long parameter lists to functions can look really ugly, we can alternatively define the parameters as part of an HLSL structure and then pass that structure into the shader. For example, in our HLSL code here, we can see that our vertex shader function takes as input a variable of type appData. We can see that this is a structure that we have defined which basically has two members. It contains a float 4, which is an HSL equivalent of a 4D vector, and we've called this variable vertex, and we also have a float 2, the HLSL equivalent of a 2D vector, which we've called UV. We can call the structures we define anything we like, and the same is true for the members of the structure. Therefore, passing appData into our vertex shader function is equivalent to our vertex function having two comma-separated parameters of type float4 and float2 called vertex and UV respectively. Using a structure like this, though, is now the preferred and more commonly used coding convention. So let's talk about the members of our appData structure and the variable types in HLSL used for containing numbers, vectors, colors, and matrices, and for that we'll pop over to the Unity documentation. So the highly mathematical nature of 3D graphics means that more often than not, in your vertex shaders and your fragment shaders, you're going to be passed data, you're going to be dealing with data, and you're going to be outputting data that is floating point in nature. The HLSL language defines the float basic data type, as you can see here, which is much like the float variable type in any regular programming language. It's 32 bits wide and has the same precision and range. However, the graphics cards of yesteryear, when HLSL was invented, weren't as fast as they are today, especially in desktop platforms. And therefore, your game could take quite a performance hit if every computation you did in every vertex and pixel shader was using a full 32-bit wide float for everything. Therefore, speed could be gained if, when you were dealing with values that didn't need that range and didn't need that exact precision, you could use, for example, a half width float. You can see here that we have the variable type half, which is actually 16 bits wide instead of 32 bits wide. As a result, has a range of minus 60,000 to plus 60,000 with about 3 decimal digits of precision. So where would you want to use a float? Well, you want to use a float where you know the numbers are going to be pretty big and you're going to need 32 bits to adequately represent them. An example would be world space positions, for example. Your world is generally pretty big, and therefore so too will your world space vertex positions. You're also going to want to use them in cases where you really need the most precision possible, the maximum number of decimal places to get an accurate computation, such as when performing scalar computations involving complex functions such as trigonometry, or when calculating texture coordinates, for example. Of course, a lot of the time we're going to be dealing with values that don't really need that much precision or don't need to store such large numbers, where the half data type comes in really handy. Like I said, the half data type is 16 bits wide instead of 32 and is ideal for representing things like high dynamic range colors or object space positions, basically vertex positions which we know aren't going to have really large values that are likely to fall outside the 60,000 unit range. Direction vectors are another good example of where you might use half precision. And there's also an even smaller float type that is 11 bits wide, which is called fixed. The fixed data type is 11 bits wide and can hold a range between -2 and +2 with 1/256 precision. This makes it ideal for dealing with standard definition range colors, for example, or just performing simple operations where you don't need the values to be sort of any greater than -2 to +2, which is actually quite a lot in 3D graphics, where we're often dealing with computations in the -1 to +1 range. There's also a third data type here called the integer data type, but I'm not going to cover it because I've never seen it being used, and I think it might not be supported on some GPUs, so I don't think it's worth worrying about. So for your basic data types, we have a 32-bit float called float, we have a 16-bit float called half, and we have an 11-bit float called fixed. Now this is where things get kind of interesting. Because desktop platforms now are so good at handling full float arithmetic, if you write a shader that uses half or fixed data types, if the platform being compiled for in Unity is a desktop platform, it will just be ignored and the float basic data type will be used for everything. So you will always have full 32-bit floats and it really just won't affect your performance. However, this isn't true with some mobile platforms. So it's kind of hard, right? Because if you're developing for a mobile platform but you're prototyping your shaders on a desktop PC, then you're not actually getting to test whether the half and fixed precision that you're using is actually doing the job properly and whether you can get away with using that reduced precision, because when you run it on your desktop platform, it's using floats anyway. So you need to be careful. If you're going to make those optimizations and use half and fixed data types, you need to make sure that you also test it on the actual device that you're building the shader for before you commit too much time and resources to it. So those are the basic data types. Well, what about composite data types? Things such as 3D or 4D vectors or 4x4 matrices, for example. Well, you can see that in order to create a 3D vector, you just use float 3, for example, and that will create a vector with 3 components, x, y, and z, where each component is of type float, in other words 32 bits wide. If you wanted to create a 4D vector at half precision, where each component was 16 bits, then we could declare a variable of type half4. This would be a medium precision 4D vector that would have an x, y, z, and w component. It's also worth noting actually that when you're dealing with vectors in this way, you can access the components using X, Y, Z, and W, or RGB or A. They're both kind of the same thing, which is really handy if you're treating vectors as color containers and things like that. So if we wanted to create a fixed precision, 11 bits precision 2D vector, we would just define a fixed 2. So what about matrices? We're often dealing with 4x4 matrices or sometimes 3x3 matrices. Once again, pretty simple. It's a composite type. So we choose the basic data type that's going to represent the precision of each of the members of the matrix, and then we append it with, for example, 4 times 4. So you can see here, for example, that if we wanted to create a 4x4 matrix where each element of the matrix had 32-bit wide float, we could just create that as type float 4 times 4. If we wanted to create a 4x4 matrix where each element was of half precision, we could declare a variable of type half 4 times 4. If we wanted to create a 3x3 matrix where every element had 11 bits of precision, we could create a variable of type fixed 3x3. So let's now look at how we declare texture variables in HLSL code. You can see we do that by using the variable type sampler2D, if we wish to declare a variable that is of a 2D texture, or sample a cube if the data we're passing into that variable is a cube map. Once we have, for example, a variable in our shader code called sampler2D, we can use either the materials inspector or we can use our own scripts to contact that shader and send data in to set that variable to the texture that we wish. So you're going to see later when we create our camera lens blood effect, we're going to kind of contact the shader and we're going to set the blood texture into that shader so that it can sample its color and blend it with the frame buffer. Okay, so going back to our input structure now, we can see that our first member is a float 4. In other words, it's a 4D vector which we're going to use to store the vertex position. Now we'll talk a little bit about semantics in a minute, but you can see that this is the semantic here. It's called position. And because we've given our vertex variable here the position semantic, Unity now knows that this is the data container that we wish it to store the object space vertex position before it passes it into our vertex shader. Furthermore, underneath that, you can see we create a float 2. In other words, a 2D vector where each component of the vector has full 32-bit wide precision. And we call this UV. And we give this text chord 0 semantic. This lets the Unity engine know that this member is what we wish to use to have the texture coordinate of the vertex passed into our vertex function. So just before the vertex shader is called by the pipeline, it's going to look at our input structure. It's going to say, I need to get the position. And of course, if you've read the material that I told you about, you'll know why, although we're dealing with 3D vectors, we actually get past them as 4D vectors with a W of 1 when we're dealing with object space coordinates. And that's so it makes all of the matrix math work out, so that we can also do not just rotations but also translations. And it will also look at this text chord here, text chord 0, and it will know that in this variable called UV, we wish it to store the first set of texture coordinates that are stored in the vertex. And a lot of the time a vertex will only have a single set of texture coordinates. So we've told Unity using those semantics exactly what data we want and where we want it stored in our structure, so that it can then be passed into our vertex shader where we can then fetch it out and do some cool stuff with it. So if you want to see all of the possible semantics that we can use in HLSL, then head over to msdn.microsoft.com. Take a look at the HLSL reference, and in the language syntax under semantics you'll see there is a big table of all of the different semantics that we can use that will tell Unity what data we want from the vertex. So for example, if we created a variable and we gave it, let's say, the color semantic, well then Unity would know that that's where we wish the color of the vertex to be stored. Now what you're looking at here are the vertex shader semantics, but if you scroll down you can also see there are some separate pixel shader semantics as well. The most common being color, which is used to describe what we're actually outputting from the fragment shader. Now there's lots of things to remember when you first get into shader programming, like all of these semantics for example, but don't worry about it. As you start to investigate people's shaders, you start to understand the code, you start to look through the include files that ship with Unity, they will start to stick, and you will kind of realize that there's not that many of them, and most of the time you're just using the same ones. So it's all very well getting data into a vertex shader, but we need to do something with the vertex position and the texture coordinate, and we need to output it. And therefore, we also need an output structure, and we've defined this structure and we've called it V2F, which is short for vertex to fragment. And the reason we've called it vertex to fragment is because the data that we output from the vertex shader will later on during the triangle rasterization phase be interpolated across the surface, and the fragment shader will actually be sent in an interpolated version of this structure so that it has the various data elements contained within interpolated for the particular fragment being shaded. So just like the vertex input structure, the output structure also uses semantics. So in the case of our vertex output structure, which of course also is our fragment shader input structure, we're saying that we want our vertex to output a UV coordinate, so we give it the text chord 0 semantic, and we also want it to output a float 4 called vertex again, but this time rather than just giving it the position semantic, we have to give it the SV position semantic, which tells the pipeline that this is being used for a screen position. Okay, so when we're dealing with geometry, we use the position semantic, but when we're actually dealing with outputting vertex data for use by the fragment shader, we use the SV position semantic. And you can see that if you go and look on MSDN in that reference that I just showed you. So let's now have a look at our shader and see what it does. Well, you can see that as it's called, it will be passed by Unity, the app data structure. It will contain the object space vertex position and the UV coordinate. Inside the shader, the first thing we do is we declare a new variable of type v2f. Remember, that's going to be our output structure. So we declare one of those so that we can now fill in the two data members with meaningful data. If you've read the material that I showed you earlier on, that I wrote some time ago for DirectX 9, or if you have the understanding of 3D transformations that you'll need, you will know that in order to transform an object space vertex position into a homogeneous clip space vertex position, we need to multiply that vertex position by the world matrix, which Unity sometimes calls the model matrix, by the view matrix, and by the projection matrix. And you'll also know, if you've read that material, that one of the things that's really cool about matrices is that we can multiply matrices together to create one combined matrix which has the same effect as if the vertex had been multiplied by all three. So rather than multiplying our vertex position by the model matrix, then multiplying it by the view matrix, then modifying it by the projection matrix, we can just combine all of those three matrices together into one resulting matrix, and then we can multiply our vertex position by that, and it has the same effect. So you can see that in order to do that, the first thing I do is I say o.vertex, because remember, we want to store the result of this calculation here in the vertex member of our v2f structure. So I'm saying o.vertex. And then we use one of HLSL's many mathematical functions. This time I'm using the mul function, which is short for multiply. This function takes a matrix and a vertex, and you can see for the vertex we're passing in the vertex position that we've been passed into this function by Unity, and as the matrix we're passing in this weird word here, Unity underscore matrix underscore MVP. This is a classic case of one of the built-in shader variables that the Unity engine makes available to our shaders. So before our shaders are executed, this model, the model to which this vertex belongs, will have had its model view and projection matrices combined so that we can access this variable and use it in our shaders. Now if you take a look in the Unity documentation, once again if we look at the writing vertex and fragment shaders section and open up built-in shader variables, you can see some of the matrices that the Unity engine makes available to our shaders. So you can see that's the one we're using, which is the combined model matrix, view matrix and projection matrix. Alternatively, we have just the model matrix multiplied by the view matrix, and we also have just the camera's view matrix if we need that, just the projection matrix. We also have the view and projection matrix combined here. You can also see that we have a variable here called underscore object to world, which is a matrix that if we multiply the vertex that has passed into the vertex shader by this, it will just transform it from object space to world space. And that's pretty useful because sometimes we want to do computations, especially of distances and things like that, in world space. We can't do everything in homogeneous clip space. Alternatively, you can also see there is a variable called world to object, which is the same as the object to world, except it's the complete opposite direction of travel. It's the inverse of the current world matrix of the object being transformed. So if we have a vector given to us in world space and we want to find out the direction of that in object space, we can use this matrix to do it. You can see if we go down, there's also lots of different built-in variables here. There's a 3D vector here that we can use if we need to get the world space position of the camera. And we also have some other variables here that are pretty useful for doing things like animation. Like for example, you can see that we have the time variable here, or we have sin time and cos time, which is good for doing animations in like a sine pattern or a cosine pattern. You can see here that there's some of the variables that we can use if we need to access things in our shader, such as what is the current ambient color of the sky, or what's the current fog color, or what fog mode has the editor been currently set into. So definitely worth checking out this shader documentation, because there's a lot of really good information there, and you'll know everything that you have at your disposal when writing shaders. But admittedly, it's very daunting when you're first writing shaders. Also, it's really worth you heading over to msdn.microsoft.com, checking out the reference for HLSL and looking at the list of intrinsic functions, such as that multiply function that we just looked at in our shader. Because there are many functions in the high-level shader language that encompass everything from simple mathematical operations such as getting the absolute value of something, to all of the trigonomic functions such as calculating the cosine, the arcsine, and the tangent and things like that. Other functions such as clamping and functions to perform cross products and dot products. And also, if I scroll down a little bit, you can see we also have functions down here, which you're going to see a lot in your shaders. This one here, text2d. This is a function that we use to sample a texture. So obviously we're going to see that being used, and you can see there's 1D, 2D, and 3D texture versions of that, and also a text cube function for sampling a texel from a cube map. So anyway, let's go back to our shader and continue on looking at the code. So we know that when we call the HLSL multiply function, we're passing in the combined model view projection matrix, and we're going to multiply our object space vertex position with it. Just this one line of code fully transforms the object space vertex into homogeneous clip space, and we don't have to do any more with the vertex position. It's ready to be output from the shader. The next line down, you can see we just simply copy over the texture coordinate that's been passed in into the output structure. We don't want to do any animation of the texture coordinate. If we wanted to, we could do it here. So if we wanted to have the effect of, I don't know, like a scrolling waterfall or something, this is where we could do it. We could animate the UV coordinates here, adding some offset, perhaps multiplied by some sort of sine function or something like that, and would output the modified result in our output structure. But for now, and it's usually the case with an image effect, it's just copying over the UV coordinates from the vertex into the output structure. And of course, when this vertex shader is finished executed, we've now passed back to the Unity 3D pipeline the new vertex position in homogeneous clip space with an unmodified UV coordinate. So we now see how the vertex shader works. Now don't worry about how we get data into and out of the vertex shader. We'll talk a little bit about that at the moment. I'm deliberately starting in the middle of this shader, and then we'll go back up in a minute and explain all this weird stuff up here. So when our shader is being used to render an object in our scene, it's pretty obvious to understand where the vertex data is coming from. It's being given to us directly from the 3D model itself. But what about in the case where we're using a shader such as this to render an image effect? Where do the vertices come from then? Well, we touched upon this a few moments ago, but an image effect will actually be implemented by drawing a large quad that consumes the entire area of the render target. And you'll see in a minute that we're going to create a monobehavior script that is a companion to this shader that we're going to add to our camera, and it's going to be that script which is going to be responsible for drawing that quad using this shader. So let's just pop over to the production version of Dead Earth for a moment and talk about that in a little bit more detail. So you can see I've got my camera selected in the inspector, and in this particular case we have a whole host of image effect scripts. Let's just assume for now that we only have one script, and it's our script, the blood behavior, or the bleed behavior as it's called here. So the way that it works is the camera is told to render its scene to its render target. Now, I'm using the term render target ambiguously here because obviously in Unity there is such a thing as a render target asset where we can create our own render target textures and tell our camera to render to those textures, and then we can use those textures as inputs to other shaders and materials. However, even when we have no render target assigned, such as is the case with this camera, you can see the render target field has none in it. Behind the scenes, Unity has its own reserved render textures that it's using as the frame buffer. And it would normally have several of these textures that it uses in a swap chain so that they can be fed as inputs into multiple image effect scripts. So let's just assume that our camera has a render texture somewhere in the background that we don't know about that it's rendering the scene to. What happens next is Unity will examine all of the scripts that are on the camera object. That's the game object with the camera component that has just done the render. And it will look for any script that has implemented monobehaviors on render image function. As you can see, on render image takes two parameters, both of them being render textures. It's in the onRenderImage function, which by the way will only be called by Unity if the monobehavior in question is on a game object which has a camera. Okay, so you can't perform image effects on scripts unless those scripts are on the camera. If you implement onRenderImage in a script that isn't on a camera, Unity will not call the function and it will be ignored. So let's just continue the assumption for the moment that we only have one image effect script that has implemented the onRenderImage function. When this function is called, it's going to pass into the function as its first parameter a render texture that the camera has just rendered the scene into. Our job in this function will be to take the data in that texture, modify it in some way, and return the new image in the second render texture that we've been provided as the second parameter to the function. Now, if we were going to do that manually, we would need to be responsible for drawing a big quad over the screen, sampling the source texture that we would pass as the first parameter, and outputting the result to the second render texture called the destination texture. However, we don't have to do that because Unity has a graphics class which has a function called Blit, which does all of that for us. In fact, if we look at the little code sample here, you can see a perfectly legitimate onRenderImage function. The source texture would contain the current image that has been rendered by the camera, and the destination texture is the texture that we need to copy that data into with any modifications that we make. We call the graphics.blit function, passing in the source and destination textures and also the material that we wish to use to render the quad over the screen. That material, of course, will be the material that has our shader assigned to it. The graphics.blit function takes care of creating the quad and also calling our material shader, and that's all that's involved in doing a basic image effect script. So what's really cool about this is when our shader is executed, the source texture that we pass into the blit function as its first parameter will actually be assigned to a sampler2D variable in our shader called main_tex. Now, we touched upon this earlier on, but in order to declare a 2D texture variable in your HLSL code, it uses the type sampler2D. And we can call our texture variables anything that we like, and via our code we can use the material classes interface to talk to its shader and set those variables to legitimate texture targets. However, there are certain variable names for sampler2D variables that have special meaning in Unity, and one of them is this one. If we call the variable _main_tex with a capital M and a capital T, behind the scenes, just as it renders its quad, will send the source texture into the shader as this variable. Okay, so that means that when we get into our fragment shader, we now have access to the image that is currently in the render texture or the frame buffer. We can then modify that image on a per pixel basis, output the result, and the blit function will make sure that the color output from the fragment shader is copied into the corresponding pixel in the destination texture. When the onRenderImage function is complete, the destination texture will now contain the current up-to-date image of what our scene should look like with the modifications made by our image effect script. Now, of course, we can have multiple image effect scripts on our camera game object like I do here. And when that's the case, they are called in order, one at a time, each one having its onRenderImage function called. The important point though is that when the first image effect is called, which in this case would be my bloom effect, it's going to be passed a render target that contains the basic vanilla rendering of the scene by the camera. It's then going to output the result of the bloom image effect in that destination texture. This destination texture then gets sent in as the source texture to the next image effect in the list, so that in our particular example here, the screen space ambient occlusion script would have passed into its onRenderImage function the image of the scene that has already had the bloom effect applied to it. We can then apply the screen space ambient occlusion to it, copy that into a destination texture, which then becomes the source texture for the next image effect, and so on. Now behind the scenes, this is probably being implemented by Unity by using two render textures that it's continually swapping between. The important point though is that we pass through these image effects in order. Each time the texture passed into an image effects on render image function will be what was output from the previous image effect above it in the image effect chain. So obviously we're going to write an onRender image function for our behavior in a moment, and of course it's on that onRender image function that you can also choose to do other things, such as send additional data into the shader that your shader needs. So we're going to see us using this script to send in our blood texture, is blood normal map, and send in the current blood amount that we would like our shader to apply. So it's all pretty basic stuff. So if we go back to the shader, we can see that having covered the vertex shader now, we also have a 2D texture variable declared called main_tex. And because we've given it that name, the graphics class's blip function will find that variable and it will assign to that variable the texture that was input into the onRender image function of our image effect. So let's have a look at our fragment shader. So our fragment shader returns a color, a fixed 4, and it takes as input our V2F structure that we described up here, which, remember, when we output it from the vertex shader, contained the UV coordinate of the vertex and the homogeneous clip space position of the vertex. Now that's not the same thing that we're being passed into the fragment shader, because the fragment shader is called on a per pixel basis. So during triangle rasterization, the values that are output from the vertex shader on a per vertex level are interpolated across the surface, and it's the interpolated values that were being passed into the fragment shader in this structure. So if you imagine we had two vertices, one that had the color green and one that had the color blue, and the renderer was rendering a line between those two vertices, halfway across the line the fragment shader would actually be called with an exact 50-50 blend of both of those colors as its color. It's also worth noting actually that when we return a color from a fragment shader, we should also give the return value this SV_target semantic. That's what tells the pipeline that it's a color that we are returning. And if you checked out the msdn.microsoft.com website that I showed you earlier on in the HLSL language reference, you'll see that there are some alternatives here, such as when we're rendering depth textures. But in the case where we're just outputting color, we always use that SV_target semantic on the fragment shader, so that it identifies to the pipeline exactly what the color we're returning is to be used for. Now inside the fragment shader, this is very, very simple, and it shows us for the first time how to use one of the HLSL functions, in this case a function called text2D, to sample the color from a texture given the UV coordinates that we've been passed in from the interpolated vertex data. So you can see that we need to store the value of this sample somewhere, so we create a new local variable of type fixed4, which is pretty much the most common value that we use for standard def colors, and we call this variable col, and we assign it the result of doing a text2D operation. In other words, this is HLSL speak for sampling a 2D texture, and as the first parameter we pass in the texture that we wish it to sample. Now in this particular example we only have one texture defined in our shader, and that is the one that has been given that magical name of main_tex. And as we saw just now, because of the way that we're going to use the graphics.blip function in our onRender image function, that function will automatically take care of making sure that this sampler 2D is assigned the texture that contains the current image of the scene. And as the second parameter, we just pass in the interpolated UV coordinates for the particular fragment in question. So if we assume that we're the first image effect in the image effect chain on our camera game object, then what we're doing is we're basically just trying to sample the color in the source texture that corresponds to the pixel in the destination texture for which this fragment shader is being executed. So we're just sampling the corresponding pixel, and if we didn't do anything else, if we just returned that color without doing this little inversion operation here, then we would essentially spit out a destination texture from our onRender image function that was exactly the same as the input texture. But you can see that's not what we do. We grab the color of the current pixel being processed from the input texture, and we invert that color by saying we want color to equal 1 minus the color. Now remember, colors in HLSL are in the 0 to 1 range, at least for standard def non-HDR colors. So yeah, this just makes sure that dark colors become light and light colors become dark. And then finally, we just return that color from the pixel shader. And in the case of an image effect, that means we're going to return this color to be stored in the corresponding pixel in the destination texture. And that's all that's to the HLS code of this very basic inversion image effect script. But of course, there's some other things that we haven't talked about yet, such as all of this stuff surrounding the shader. This is actually a declarative language called ShaderLab that is particular and specific to Unity. So let's talk about what ShaderLab is. So when we develop a shader in Unity, the HLSL section that we've covered already and describes how we implement our vertex and fragment shaders, they certainly describe in a detailed way to an engine such as Unity how the vertices of our scene should be transformed and how the colors of the pixels rendered should be calculated. However, there are many more stages in a game engine than just transforming vertices and coloring pixels. And these stages exist in a kind of black box. It's not something that we can change directly from HLSL code. If we wish to change the behavior of these stages in order for our triangles to render properly, we need to set or unset states in the engine. Such an example would be, do we wish to use the depth buffer or not? And normally when rendering the objects in our scene, we definitely want to use the depth buffer so that objects that are further away are obscured by objects that are closer to the camera. Furthermore, if our shader is supposed to be rendering a transparent surface, such as glass or water or something like that, then we don't want the colors output from our fragment shader to simply overwrite anything that's already in the frame buffer. Instead, we wish to perform alpha blending so that the colors we output are blended to some extent with the colors already there. Now, if you read that material on the Game Institute website that I told you about earlier on, there's a big discussion of how alpha blending works and the various alpha blending operations available in DirectX 9, and they're all available in Unity as well. Furthermore, it's generally the case that when we are rendering a scene, half of the polygons in the scene will be facing away from the camera, and therefore we don't want to waste any time processing faces that we can't see. It's normally the case that objects are authored such that when the triangles of the object have a counterclockwise winding order, they're considered to be facing away from the viewer and can be discarded. However, that's not always the case, so we could come across a situation where we've been given a model where the winding order of the faces is reversed, and we may wish to change how the engine performs its backface culling process. Furthermore, in the case of an image effect, we don't want to use a depth buffer at all, because we just want the quad that we're drawing to be rendered always over the top of what's already in the frame buffer. And with respect to culling, well, we know that when this shader is going to be called, it's being called by the graphics.blit function, which will already be providing us with a quad with the correct winding order. So in this particular case, we would want to turn backface culling off because it's just a test we don't need to do. And any tests that we can eliminate will surely make our shaders more efficient. But there's also other things to consider as well, such as how our shader is going to integrate with the Unity editor. And if we go back to our project, and I'll just select that temp material we created, we can see, for example, that each shader is given a name that can be displayed in a drop-down list, so that when we create a material, we can choose which shader we wish to use for that material. We're going to want any shaders that we create to show up in this list as well. Usually, however, we don't actually want image effect shaders to show up in this list. There's no problem with them showing up in this list. It's something that we can control. But you'll notice if you import many of the image effects that ship with Unity, their shaders are not actually displayed in this list. And that's because when the shader is created, we use ShaderLab to tell Unity that we want this to be a hidden shader. And that's because the shaders that are written for image effects are normally very different beasts to those that we would apply to objects in our scene. And usually when we're setting up materials as assets in our project, we're actually configuring them so that we can drag and drop them into objects in the scene. What normally happens with image effects, and this is how I'm going to implement it, is I'm going to have the shader itself hidden so it doesn't show up in this drop down, and in the mono behavior itself that we're going to add to the camera, we'll create the material programmatically and assign the shader to it there. Just because the shader is hidden doesn't mean we can't use it in code, but it does mean it won't show up in this drop down. And of course, the other thing that Unity has to cater for is the fact that different shaders have a varying amount of shader inputs. For example, we can see that the standard shader has lots of different inputs, many of them textures, but if we go to, say, the legacy diffuse shader, that just has a single texture slot with tiling and offset values. And if we go to, say, the skybox and choose the six-sided material, you can see that this has two float values that we can tweak, a color value that we can use to tint the color of the skybox, and also this time 6 slots for textures that obviously become the 6 sides of the skybox. So depending on the shader that we assign to a material, the inspector of that material needs to change to reflect all of the shader variables so that we can then assign resources in our project to those variables that will be passed into the shader. So to accomplish this, Unity Technologies created a declarative language, kind of like a shader presentation framework, which allows us to present the shader to the engine such that before the shader is invoked, we can configure all the various states of the engine, and also a way for us to present to the editor how a material using the shader should have its inspector configured so that we can, via the materials inspector, set up the inputs to the shader. If I zoom out here, you can see that the very first line in a Shader Lab shader has to use this shader keyword followed by the name of the shader, and we'll come back to that in a minute. But then all of what follows is contained in the curly braces of the shader block. Okay, so we're saying here that here is a shader and we want this shader to be called hidden/camera blood effect. Now the name that we give to a shader can be anything that we like, and it uses very much the path syntax. So if we wanted to instead create our camera blood effect such that it shows up in the drop down as being in a Game Institute submenu, we could change hidden here to Game Institute, like so. Now if I save that off, go back to the editor, and with my temp material selected, now go to the shader drop down for this material, notice there is now a Game Institute submenu, and in that is our camera blood effect. So any name that we give it, or any path that we give it, will determine how it shows up in this inspector dropdown. However, we did say we don't want the shaders for our image effects to show up, and when we don't want them to show up in the dropdown, we can just append the name with hidden /, and that basically means if I go back now, you'll see that it isn't showing up in the dropdown. That's how we hide shaders, so we stop people accidentally selecting them when setting up materials for objects in our scene. For now though, I'm going to go back and I'm going to change that to Game Institute again, just so we can see when I start messing around with the properties block in a minute, how that affects the materials inspector. So once again, if I go back, pull down the shader drop down, you can see we now have that Game Institute submenu, and we've got it called camera blood effect. So we could assign our camera blood effect to this material if we wanted by simply selecting it like so. What we could do instead, it doesn't need to just have a single submenu. We could create it in the Game Institute image effects submenu like so, and I think I'll put a space between Game Institute, save it off, go back, and we can now see that in the drop down we've got the Game Institute submenu, we've got an image effects submenu, and in the image effects submenu we have our camera blood effect. If we dragged and dropped this material now onto the objects in our scene, it wouldn't make a lot of sense because this shader isn't meant to be a shader that we add to objects, but we would see the results change. It would have very strange results indeed. So let me just add it to the floor. You can see it just goes black. Doesn't look too good, does it? That's because we haven't assigned any texture yet to it. So you can see inside the shader block, one of the first things we normally do is we declare a properties block. The properties block allows us to describe to the Unity editor which variables we wish to show up in the inspector. They're called properties. They're not actually the shader variables, but they're our means of mapping resources that we assign in the materials inspector to the variables in our shader. So in this particular case, we are defining a property called main text. And a property always follows this sort of similar syntax. So we have the name of the property, and then we have the parentheses that follow it, and the first parameter in the parentheses is the display name for this property, which in this case is texture, and followed by the actual type that this property is supposed to represent, and that's going to have to match a variable in our shader, which I'll get to in a minute. In this particular case, we're saying that this is a type 2D, and a 2D property is basically a 2D texture. So the first important thing here is that the name of the variable is very important, and it should match a variable in our HLSL code with the same name and of the appropriate type. So for a property called underscore main text, which is of type 2D, which remember it's a 2D texture, there should also be a variable defined in our HLSL code with the same name and with the correct type, which in HLSL code is a sampler 2D. So this is how Unity makes the mapping from the texture that we might assign in the inspector and how it matches it to the actual variable in our HLSL code. So the names have to match exactly, and they have to be of the correct type. We'll have a look at the documentation in a minute, and we'll look at some of the other types of properties that we can create. The first parameter in the parentheses though is the display name. Just because this property is called underscore main text, don't necessarily want that to be the thing that shows up in the inspector. So you can see here by default main text is given the display name of texture, and if we go back to the editor we can see that that is indeed the case. This property is called texture in the materials inspector. If we change that to source texture, you can see that it's now changed to source texture there as well, which is pretty cool. So let's just put that back to texture for now. Like I said, that's not used for anything else other than to make the inspector look nice with a nice display name. You can also assign any property a default value. This makes a lot more sense in the case of when we're defining properties for floats and integers and things like that. But for textures, we can assign it a series of colors, and I think they're all listed in the documentation somewhere down here. Yes, I'm on the Shader Lab properties page here. If you scroll down, you can see there are a few default colors that we can assign a texture: white, black, gray, bump, and red. But we don't have to worry about that. So while I'm on the Shader Lab properties page, you can see here some of the different types of properties that we can create. For numeric quantities, we can create a property that is of a range where we get to specify min and max, and what that will do is show up in the inspector as a slider, which is normally much nicer to work with than just having a float box. Or we can declare it to be a float, so it will show up in the inspector as just a box that we can type a floating point number into, or an integer, where it will show up as a box we can type an integer number into. For colors and vectors, we just use the color type or the vector type. And for textures, as we've already seen, for a 2D texture we use the 2D type, for a cube map we use the cube type, and for a 3D texture we use the 3D type. So looking at that, let's just, so we can test that properties work, let's create another property in our shader, and we'll call this one blood texture, and I'll give it a label of blood texture in the inspector as well. This is also going to be a 2D texture. I'll just assign that the same default value, like so. If I save that off, we should see the material inspector change, and there you can see we now have two textures in our material. Now, of course, if I assigned anything to that blood texture at the moment, wouldn't actually do anything, because although we have it defined as a property, there isn't actually a sampler 2D variable in my HLSL code with the matching name. So if I wanted the texture to actually be useful, I would also have to create a sampler 2D with exactly the same name, and this is case sensitive, by the way, guys, all right? So I would do that like so. And then the textures that I assign to those two slots will automatically be used to fill out the main text and blood texture sampler 2D variables in the actual HSL code. But we're not going to do that for now, so I'm going to delete that. I'm also going to delete my blood texture. We will be doing that later on, but for now I just want to concentrate on this default camera effect. So let's see how we would create a float property. So we might call this, I don't know, blood amount, and we might give it a display name just of amount, and we would give this the float type, and we might say by default we'll give this a value of 0.5, like so. Save that off, go back to the editor, and you can see we now have a float box in our materials inspector. But once again, if I wanted to actually use this blood amount in the actual shader itself, I would have to have a variable of type, I don't know, say fixed or float. Could be any one of those. Let's say float, and I would have to give this exactly the same name, which was blood amount, like so. Oops, I used two underscores there, and that's how Unity knows that when this shader is executed, that the amount that we've assigned to its material via this property needs to be fed into the shader in this float variable here. So once again, I'm going to delete those, and just for one more example, let's change our blood amount to a range value instead, and let's get a range of 0 to 1 like so, the default value of 0.5. Go back to the editor. You can now see that our amount has been replaced by a nice cool UI slider, and you also should have seen there that the default value was at 0.5. But I'm going to delete all of this stuff from the shader now, not the main text, because that one's vitally important. Okay, all image effects have to have a property called main text and a sampler2d called main text, because as described, that's what the graphics class's blip function expects our shader to have when it needs to pass into our shader the source texture that we wish to sample from. Okay, so that's how properties work. So following the properties block, you can see we have a block called subshader. Now, if you've done any programming with DirectX or with effect files, subshaders are analogous to techniques in Microsoft's effect files. It's often the case that you're going to be having your shader or your game execute on a wide variety of 3D hardware, and perhaps even a wide variety of platforms. And those platforms and the hardware will not all have the same capabilities, so it's pretty likely that sometimes you'll write a really complex shader that may not be able to be executed on all of the hardware that your game is running on. The way around this is we can create several subshaders within a given ShaderLab shader. And when this shader is invoked at runtime, Unity will basically start at the top with the very first subshader defined, and it will try to find the first subshader that is capable of running on the hardware that your game is currently running on. And if it finds that there are some really sort of advanced techniques used in this subshader that isn't supported on the hardware that it's running, well, then it will try to find the next subshader in the list. So this allows you to make really cool shaders that use all the very latest features of graphics cards, but still have a fallback with much more simpler subshaders that will be used when this shader is being used on older hardware. Now, in our image effect, we're not doing anything special, so we've just got a single subshader. This is pretty much guaranteed to work on every sort of piece of hardware that's around today. But that's how you would do it. So a subshader is essentially the shader that we're going to use on the particular hardware on which it's running. Furthermore, there's also another fallback technique if for whatever reason none of the subshaders in your shader work on the current hardware. And we do this by putting it outside of the subshader, any of the subshader blocks, and we can use the fallback command like so, and we simply specify the name of the shader that we wish to fall back to if none of the subshaders in this shader are able to be executed on the current hardware. So if I go back to the Unity editor and go to one of the old I don't know, legacy shaders, I suppose, we could use diffuse. So if I was to say diffuse like so, then if I were to execute the shader on a machine that just couldn't execute any of the subshaders that I've created, then it would just fall back and use the diffuse shader that comes built into Unity as the fallback shader to use. So that's pretty cool as well. Not normally something that we use in image effects, but definitely something that you use as a kind of catch-all option when you're developing more standard shaders for use by materials on your objects. Oh, actually guys, my example there of using fallback was erroneous, because I forgot they've actually moved the old legacy diffuse shader now. Its actual name isn't just diffuse, is it? It is, let's have a look. It's in legacy shaders / diffuse. So if I wanted to fall back to that diffuse, I would need to actually specify its name like so. Was it a capital D? I can't remember. God, my memory's terrible. Yes, a capital D. So that's how we would fall back to the old legacy diffuse shader if we wanted to. Of course, it would look crap, but it's at least your game would run. But like I said, we don't need that for image effects. Also, it's worth mentioning that one of the best learning resources that you can have is to go to Unity's website, go to the Unity download archive, and for whichever version of Unity you're using, and on whichever platform you're using, you can actually choose to download the source code to the built-in shaders that ship with Unity. This will download all of the shaders used by the Unity engine so that you can open up and look at their HLSL code. One other thing that is worth pointing out is that it's often the case that there are certain shaders that are used by Unity. If you wish to replace one of these internal shaders, you just have to create a shader with exactly the same name as the built-in shader, and that will overwrite the built-in shader. So this is pretty useful. I don't know if it's still the case in Unity 5, but back in Unity 4 you didn't have any access to changing the shader that was used for the terrain. I don't think you could even change the material that was used. So the way that you would create your own custom terrain shaders is you would basically just download the built-in shaders from Unity's website, open up the terrain shader, and first of all that would give you the exact name of the terrain shader, which might be hidden/terrain, and then you could change the code in there, and because it had exactly the same name as the built-in shader being used by the terrain system, it would overwrite the one that Unity was using, and you would be able to replace it with your own. So that's how you create your own shaders to replace some of the built-in shaders. So inside the subshader block, remember, a subshader is essentially a technique. It is the shader itself that's going to be used. So like I said, if we have multiple subshaders, they're not all going to be used. Only one of them is going to be selected for use on the current hardware. So inside the subshader, we have a number of things. First thing we have is we have a series of states that we can set to configure the engine. So you can see that in the case of an image effect, we normally turn back face culling off. Like I said, we know in the case of an image effect, we're being passed the geometry by the graphics class's blip function, so we know it's going to be facing the right direction and the winding order is going to be correct. So it's pointless doing any culling or the processing that's involved in that culling, because it's just going to waste time. Furthermore, because we're just processing pixels in a render target, we don't want to do any Z writing, okay? We wouldn't want to have our image effect write to the Z buffer and then find out that another image effect, which is also sort of testing the depth buffer, wouldn't work. So you can see I turn Z writing off, none of this gets written to the depth buffer, and I always set Z test to always, because of course when we're rendering objects normally, we only let fragments through that have a Z buffer value that is smaller than a pixel that is already stored there. Pixels that are further away from the camera will have greater Z depth values. So normally we would set this to less or equal to. But by setting it to always, we're just saying, hey look, whatever is there, we want to overwrite it. We don't want to do any Z testing. In the case of an image effect, or in case of this image effect, there's actually nothing of any worthwhile in any sort of depth buffer or anything like that. So we're just turning off everything that we don't need. Let's go to the Unity documentation and look at the shader lab sort of tags and states that we can set up. So you can see that in the case of culling, we set ours to off, but it can be set to cull back or cull front. Cull back is the normal one that's used. We'll cull any polygons away that have the vertices in a counterclockwise winding order. But if we have our vertices coming at us in a way that it has a clockwise winding order, or for whatever reason we actually want to render the backs of polygons, we could set this to front, or in the case where we want to render two-sided polygons, we could set that to off as well. Here you can see the variable modes that we can set for the Z buffer algorithm. Like I said, we set it to always in our image effect, which basically means that there's going to be no Z testing happening. We're always going to write the output of the fragment shader to the rendered target. Z writing, whether the pixel we output actually writes its depth to the depth buffer, can either be on or off. We've turned it off. And if you go and have a look at this page, it's under shader lab :pass. You can also see some of the other states that we can set. You can see here, this is how we set up alpha blending, if we want to do any color blending of the fragment that we output from our fragment shader with any image that's already in the render target. We don't do that, but if you read that documentation that I showed you on the Game Institute website, all of the same source and destination, color and blending modes apply in Unity as well. We also get to set up the alpha testing state of the engine as well here if we want. And if you don't know what any of that means, then like I said, you need to go and read that material, because we talk all about that in there. So no culling and no depth testing. Okay, so the next thing you'll see is our actual HLSL code is contained within a pass block. Now we only have one pass block in our subshader, but it's quite often the case that some shaders will require that in order to create the correct effect
of the triangle or the fragment in the color buffer. We actually have to render the object multiple times. I mean, one example of this is the terrain system in Unity. Now, in a given pass, just because of the limitations of the graphics hardware, we can only render 4 splat layers at a time. So if you decide to, for example, add 8 different base textures to your terrain, that's going to use 2 splat maps, and the way that works behind the scenes with Unity's built-in terrain system is it will have its own pass for each splat map that it renders. So for each group of 4 textures that you assign to your terrain, a separate pass will be invoked. And with each pass, the output of that pass is then color or alpha blended with what's already in the frame buffer from a previous pass. But like I said, in this particular case, in the case of an image effect, we only need 1 pass. So you can see inside the pass block is our HLSL shader code. Okay, so that's been a little bit of a lightning whirlwind introduction to writing vertex and fragment shaders in Unity. But like I said, with the documentation that I provided with you earlier on, it should be everything that you need to progress with this lesson. Okay, so why don't we create the mono behavior that we're going to later use for our camera blood effect. But for now, what we'll do is we'll add it to our camera, and we'll get it to use this camera blood effect we've just created, which of course at the moment isn't a camera blood effect at all. That's what we've just called it. But what it's actually going to do is invert the colors of our scene. So in order to do that, I'm going to go back to the Unity editor, pull up the game view, and I'm actually going to delete that material that we created, because I only created this temporary material to show you how properties work. Okay, we don't actually need it. We're going to create the material programmatically, and I'm also now going to go back to my shader, and I am going to change the name to hidden / camera blood effect, so it no longer shows up in the material drop down, because like I said, it doesn't make a lot of sense having our image effects show up there. So we created our mono behavior script, didn't we? In fact, I think we even added it to our camera, didn't we? Let me select our camera in the scene hierarchy. Yes, there it is, camera blood effect. Doesn't do anything at the moment, but we're now going to add some code, primarily the on render image function, to this script, and we're going to get it to use that shader that Unity created for us, the one we've just been exploring. Okay, so our mono behavior is going to need to create a material, and it's also going to need access to the shader that we wish to use. Now, one way that I could do this is, instead of deleting that material that I deleted just now that had the shader assigned to it, I could literally have left it as an asset, and then I could have created a public material property in this class, and then I could have hooked it up via the inspector, and then this script would have access to that material and its shader. But I really just don't like having the material for an image effect hanging around in my project, because someone may erroneously think it's a standard material that they can drag onto an object. So what I used to do before it got deprecated by the folks at Unity Technologies is I would simply do it all in code. I would create in my mono behavior a new material, and into the materials constructor I would pass in the name of the shader. So we would just say new material, and then we'd pass in that, and it would find it, create the material, and then everything was automated behind the scenes. We didn't have to bother hooking anything up. However, things have changed. For whatever reason, Unity have decided not to continue that type of constructor for a material. So what we have to do is actually hook up the shader reference as well. So let me delete the start and update functions. We don't need that stuff. That was just the boilerplate stuff created by Unity. So one of the things we're going to need is a reference to our image effect shader. So I will create a private variable of type shader. I'll call it shader with an underscore. I'll set that to null, but what we'll do is we'll serialize this field so it shows up in the inspector, so we can drag and drop our image effect into it. Now we're also going to want to create a material in this script using that shader, but I don't need the material to be serialized. We're just going to create it behind the scenes in our code. So I'll create a new private member of type material, and I'll call it material and set it to null by default. Right, so now what we're going to do is we're going to implement that on render image function, which Unity is going to call after the camera has rendered the scene. Remember, this function will not be called if this mono behavior has been added to a game object that doesn't have a camera component on it, okay? So the onRenderImage function takes two parameters, both of type renderTexture, source and renderTexture. I'll call that dest, like so. And then what we'll do inside the onRenderImage function is we will check to see if material is null. If it is, then it means this is the first invocation of this function and we need to create the material. So I will say if material equals null. Actually, what I'll do first of all, I'll say if shader equals null, then return, because that means we have forgotten to hook the shader asset up in the inspector. And we'll say if material equals null, then let's create that material using the shader. So we say material equals new material, and as the parameter to the constructor we will send in our shader reference, and that should be our material properly created. Underneath that we'll just say if material still equals null, then it means that the shader perhaps failed to compile or something like that. So we'll just return if for whatever reason the material could not be constructed. So what we'll do now is we will use that graphics classes, a blip function, to essentially render the quad and perform our image effect using our new material. So the blip function takes as its first parameter the source texture that we've been passed, as the second parameter the destination texture that we've been passed, and as the third parameter that new material that we've just created that uses our image effect shader. Now if I save that off, we need to go back to the editor now and we need to hook up that shader reference. So I'm going to drill down into my shaders folder. Remember, you should have your main camera selected at this point, and I'm going to select my camera blood effect shader and just drag and drop it there onto my camera blood effect script. Now nothing's happened at the moment because this script doesn't execute in editor mode, so we'd have to press play to see what it looks like. And there you go. There is our inverted image effect working. Pretty cool stuff, huh? If you wanted to see this working even when we're in editor mode, then you can simply go back and above the class definition you can say execute in edit mode, like so. Save that off. If we go back now, even when we're not in play mode, you can see that our image effect is working, and that's because Unity is being told behind the scenes, even when the game's not playing, to still run that onRenderImage function whenever the image needs to be updated. So congratulations, you've just created your first image effect script. Let's go back to our image effect script now, just so we can understand the fragment shader. So I did say earlier on that if we omitted this calculation here that inverts the color of the source texture, then we would essentially just be sampling the source texture, main text, and outputting the exact same result into the destination texture. So let's check that. If we comment out the bit that actually inverts the color, we're just going to be left with what we had before. Technically, there is an image effect running. It's just the image effect is taking the image that's in the render texture that the camera rendered, and it's just copying it over into the destination texture. So we could, for example, if we wanted to do something pretty horrible, we could just return a fixed color. So I could say, I want to return a fixed 4, and we'll make it red. So it'll have 1 in the red channel, 0 and 0 in the green and blue channels, and 1 in the alpha channel. And if I save that off now, we should just see that when our image effect runs, it's just a big block of red. Not very useful, but hopefully you can see that that's all this fragment shader is doing. It's just outputting colors. Okay, so let's do something a bit more fun and change this image effect so it's no longer a color inversion image effect, but it's actually an image effect that will turn our scene black and white, or grayscale. And you will remember earlier on when we took a little peek inside the Unity CG include file, you can see it has this really useful function called luminance, and we pass it a 3-component color and we get back a single value, a half precision float, which describes the luminance of the pixel, the luminance of the color, if you like. And we can then take this single value and turn that into a color where each component is just the value that's returned from this luminance function. So let's see how that would look. So the first line is unchanged. We still want to sample the color that's currently in the source texture because that's the color that we wish to find a luminance value for. So let's delete the bit where we actually invert the color of the screen, and this time we'll call the luminance function. Now the luminance function returns a single float value of half precision, so we're going to need to create a half variable type in our shader just so we can store the result of this. So we will create a new variable of type half. I'll call it lum, short for luminance, and then we will call that luminance function. Now you're probably thinking at this point that we can just take the color that we sampled from the source texture and send it unmodified into the luminance function. Now it doesn't matter, okay, that the luminance function is expecting a color with half precision components, and we've sampled our texture using fixed precision components. It doesn't matter. The compiler will automatically take care of casting upwards or downwards to match the precision. What does matter, however, is that the color that we've sampled from the texture is a 4D vector or a 4-component color, and the function expects only to be supplied 3-component colors. And that's because an alpha value makes no sense in the case of calculating luminance. Now, this can be very easily solved. In HLSL, if we only wish to send in some of the components of a color or a vector, we can simply do this: X, Y, Z. So we're telling the shader compiler that we only wish to send in the X, Y, and Z components of our 4D vector as a 3D vector, and that will totally solve that problem. If we wanted to send the X and Y components into a function that only expected to get a 2D vector or a 2D color, we could just do that. We can also swizzle the order around as well, but that's a conversation for another day. So now we know how bright this pixel is, or the luminance of this pixel. So now all we have to do is return a color that has this luminance value in each of its components, and one in the alpha channel. So we'll say return fixed 4, and the red component will simply be the luminance value, the green component will simply be the luminance value, and so too will the blue, and we'll just return 1 as the alpha value. And this should totally make our scene. I've made a mistake somewhere. Constructed too many arguments for return. Oh, that should have been fixed 4, not fixed 3. Okay, I'm hoping this will solve the problem. And there you go. There is a black and white render of our scene. Dun, dun, dun. Pretty cool stuff, huh? And just to, check it's definitely working, let's go to our camera script. Where's our camera? Oh, I need to call up the inspector. You can see if we turn off our image effect, we see it go from color to black and white. So now you should have a much better idea how image effects work. We've actually created one. Well, actually, we've created 3, right? We've created one that inverts the color. We've created one that just made the screen go red. And we've created another black and white effect. So I'm going to leave it there for this lesson because this has been a really long lesson. And when we come back in the next lesson, we'll finish off actually creating the blood effect itself. We'll change this shader into the actual effect that we want it to be. I know this has been an absolute whirlwind introduction to shaders, but I just don't have the time in the Dead Earth course to spend any more time than this, bringing you up to speed with 3D transformations, lighting, and shaders. So do read that material if you have found this lesson a little hard to follow. Thanks for listening, guys. I'll see you in the next lesson. Bye bye now.